Let's look at a problem involving a refrigeration cycle. The refrigerator shown in figure P2.67 steadily receives a power input of 0.15 kilowatts while rejecting energy by heat transfer to the surroundings at a rate of 0.6 kilowatts. Determine the rate at which energy is removed by heat transfer from the refrigerated space in kilowatts and the refrigerator's coefficient of performance. So let's look at a schematic of this refrigeration system. At the heart of it, we have this refrigeration cycle, and it receives a steady power input, we'll call W dot, that drives the refrigeration cycle. And this causes energy to be transferred at some rate, Q dot C, from the refrigerated space to the refrigeration cycle. And the refrigeration cycle then delivers energy to the room air at a rate of Q dot H. Our given data is that Q dot H is 0.6 kilowatts and that W dot for the cycle is 0.15 kilowatts. And we want to find Q dot C, that is the rate of cooling from the refrigerated space. And we also want to find the coefficient of performance of this refrigeration cycle. Now let's look at a closed refrigeration cycle energy balance. We'll do this at first with just energies and not rates. We know that a closed system has an energy balance of delta E is Q minus W. And delta E for any cycle is 0. And so we have 0 is Q minus W. But Q is really the sum of all heat transfer terms in the system. And in this case, we've got QC and QH, and so Q, we can replace this Q with the sum of QC and QH. Now we've got to be careful about signs here. QC delivers energy to the cycle, so it will be taken as a positive. Then we're going to add to that QH, but QH removes energy from the cycle, so it will be taken as a negative. And so we've got Q is equal to QC minus QH. And we'll put QC minus QH in for Q in our energy balance. So we have 0 equals QC minus QH, and then we have this minus W. Okay, so W though how is shown delivering energy to the system, and so it is taken as a negative, and so we're going to subtract a negative. We can rearrange this as W is QH minus QC. And you may recall from our last lesson that this is the same equation we got for a power cycle. So W is QH minus QC works for all power and refrigeration cycles. Now we could have gotten the same thing if we had derived this equation for energy rates. We would have said dE dt is 0 for a steady state operation, and that's equal to Q dot minus W dot, and it would have gotten us to the same place. That W dot is equal Q dot H minus Q dot C. I'll leave this exercise to the student. Our given data is that Q dot H was 0.6 kilowatts and W dot is 0.15 kilowatts. And our energy balance says that W dot is Q dot H minus Q dot C. And we want to solve this for Q dot C because that's our unknown, the rate of cooling from the refrigerated space. So Q dot C is Q dot H minus W dot. So solving for Q dot C, we get 0.6 kilowatts, which is Q dot H, minus 0.15 kilowatts, which is W dot. We get Q dot C is 0.45 kilowatts. Let's look at the coefficient of performance. Refrigeration cycles, we like to use beta as our symbol for the coefficient of performance. And the COP is simply what we want to get divided by what it costs us to get it. Well, what we want is the rate of cooling from the refrigerated space. Well, that's Q dot C. And what it costs us to get it is the power input to the refrigeration cycle. So we can say that beta, the coefficient of performance, is equal to Q dot C, which is calculated to be 0.45 kilowatts, divided by the power input to the refrigerator, which is 0.15 kilowatts, and we have a coefficient of performance, beta equals 3.0. And what that means is for every unit of energy we put into the refrigerator, we get 3 units of energy transferred from the cold space.